This is A21 Physics 4, and these are past paper solutions to simple harmonic questions that you'll find in your booklet. And they range from 2004 up to 2010. So this is question 4 from Jun2004, from Physics 4 A21 that is. Your data and formula sheet gives the following equation for the displacement x of a particle undergoing simple harmonic motion. X is equal to x naught omega t cos omega t. State what the quantities x naught and omega in this equation stand for. Give a possible unit for each. So x naught is the amplitude of the motion, or of the oscillation, and its unit then is in meters, millimeters, centimeters is acceptable in the mark scheme. Omega is the angular frequency, and its unit then is in radians per second. And they also, in the mark scheme, they will accept degrees per second as well. Figure 4.1 is a graph of a cosine function of time t. You may assume that the axes are calibrated suitably. Describe how you would use figure 4.1 to determine the value of omega for this function. Now, we know that omega, I'll write it here actually, omega is 2 pi over t. So you have to determine t from the graph. And therefore t is going to be the length of time taken between, say, one peak and the next. And so we're going to read that value of t from the graph, and that's the time period of the oscillation. And therefore, to calculate omega, so they're suggesting that in your explanation you say determine value for t, and I'm writing C graph, and then calculate omega equals 2 pi divided by t, and that gives you your answer, and that's how you get your 2 marks there. Part B, now this equation isn't used anymore, and you don't have to do it, but it doesn't do you any harm to have a wee look at this, because they've given you the equation and they're asking you to work with base units, and this is the kind of thing you could get in some kind of comprehension or data analysis exercise, so it doesn't do you any harm to do it. So it says consider the SI base units on each side of the equation. It says the equation is homogeneous, and then prove that the right hand side is homogeneous with the left. So t is equal to 2 pi over 2 pi the square root of m is the mass of the spring, and k is the spring constant. Now we can determine a unit for the spring constant using Hooke's law. F is equal to kx. So therefore k is f over x, and F is equal to its mass by acceleration, so it's kg ms to the minus 2, and x is in meters, and therefore the meters cancel out. So the units of k are kg s to the minus 2. So if I write the equation down, square root of m over k, and I split it down halfway down the page, this is in seconds, and we're suggesting that that should be equal to the units of the square root of m over k. And so we're ignoring that, so we're saying m over k, m is measured in kilograms, and k is in kg s to the minus 2. And it's a square root of that. I'm going to write it as in terms of a half. So those two go out. Bring your s to the minus 2 up to the top line, you get s to the minus 2 to the power of a half. Sorry, you get s to the plus 2 to the power of a half, and that of course then works out to be s, and therefore the equation is homogeneous with respect to units. Part C, you can do a loaded helical spring fixed at its upper end to support, which may be moved up and down at different known frequencies, may be used as a way to introduce ideas about resonance and damping. Write a short account of an experiment. To demonstrate the frequency response of this system, you need not describe the arrangement of apparatus, but your account should include a description of the procedure to be followed, and description of the observations, and an explanation of how these demonstrate the phenomenon of resonance and damping. Use sketch graphs to illustrate your answer. Now this is a kind of question worth 5 marks that you really should learn an answer of to, and you'll ensure yourself that you'll get the 5 marks, and then it becomes an easy question as opposed to a difficult one. So to answer the first bit of the question, a description of the procedure to be followed, well really what you want to do is vary the frequency and look at the sizes of the amplitude. So vary frequency from, let's say, a low to high value, and then observe or measure the amplitude. So that's your 2 marks there. That's your 2 marks already for the first part of the question. You haven't got much space here anyway to write a whole lot, so obviously they're not looking for a very, very detailed thing. So there's 2 marks for the first bit. And that question has come up a number of times. You'll see it again. And when you see it, just make sure that you write down something very similar to that. Part 2 then, it says, describe the observations and an explanation of how these demonstrate the phenomenon of resonance and damping. Use sketch graphs to illustrate your answer. And so the observations, first thing you should draw probably is your little graph. And your graph shows amplitude and driving frequency. And you show the natural frequency, and then you show the peak, like the graph that I showed you. Now, whenever that's damped, that one there's undamped, that peak is much lower and wider. In some of these mark schemes, you'll see that they're suggesting that the peak should be overhead F0, but in all the old textbooks we used, the peak was moved slightly to the left. And so recently in 2010 there was an answer, and they suggest the peak should be moved to the left, but all along in all the other answers they've actually given the peak just being directly beneath this one, which isn't just completely right. So I'm just going to draw it a little bit wider, and I'll just kind of leave it that it doesn't really look like it's neither at F0 or that it's not away from it too. So this one here is damped. The green one is the damped one. And so a very brief explanation of that will get you your marks. They're suggesting that they'd give you 1 mark for that graph. And then, so you should be saying, when frequency increased and driving frequency, or force frequency, driving frequency, equals natural frequency, then you get the largest amplitude. And so there's a mark for that. And then the last mark then saying something about when it is damped. And the way they've described this in some of the mark schemes, and it's quite a good way to describe it, you get a broader frequency of response, broader response frequency, BROA, broader frequency of response. And that means, if I just show you what that means on the little graph, here this is quite narrow where the peak is, but here it's quite wide, and that's what they mean. And that will definitely get you your 5th mark. So that actually, if you can learn that off, that becomes quite an easy question to answer.